Hello everyone. Thank you for joining this webinar on the development and real-time testing of controllers for VTOL and conventional aircraft. My name is Yves Gerster and I'm the Aerospace Industry Manager at Speedgoat. This setup could stand in your laboratory and be used for real-time testing of a flight controller. In this webinar, I will go through the development steps of control hardware and look at the verification and testing aspects that are essential for airborne equipment. To start, I will provide an overview of the challenges we face in the aerospace market when it comes to the development and testing of controllers. We will then examine the model-based design workflow required for successful real-time testing and quickly cover rapid controller prototyping and hardware-in-the-loop testing concepts to ensure that we are familiar with the most important concepts. Throughout the webinar, I will provide examples to illustrate how these concepts look like in real life. Finally, I will highlight how model-based design can assist with validation and certification, which is crucial for most aerospace companies. Key market trends show that the aerospace industry is moving towards a more sustainable and electric aviation. The emergence of new concepts such as eVTOL and UAVs is happening almost every month, while conventional aircraft features are constantly being updated. As the connectivity between aircraft features and among aircraft increases, the complexity of system integration also rises. To become a commercial product, these technologies must be certified. New, faster, and more reliable methods for testing and certification are needed due to the increasing number of requirements and high-quality expectations from customer and stakeholders. How can real-time testing help you to reduce costs? If you take a look at where errors are typically introduced and where they are detected, you will see that most of them are introduced at the beginning of product development. However, most of them are only detected at the end in the testing phase. And even worse, if an error is not detected in the testing phase, it gets really expensive. However, if you can start testing your specification on the very left side, fixing errors is much cheaper. Bugs are mainly introduced when defining the requirements and specifications, which is a difficult process to automate. The elimination of these bugs depends heavily on unit testing. Some bugs may only be found during integration or operation in the field. As you've seen in the diagram earlier, the later a bug is found, the more expensive and time-consuming it is for the whole development. Therefore, you want to identify this late error as early as possible. The best way to do that is to test the requirements and design model of the controller early on using desktop simulation. This allows for the early identification of many bugs in the design process. It is essential to test on the actual hardware as early as possible. These are the key benefits you get from using Speedgoat test systems. The target machines allow you to perform rapid controller prototyping and hardware-in-the-loop testing of your controller at the very early design stage. We will have a closer look at those two topics shortly. To understand the benefits of real-time testing, it is important to talk about model-based design first. For this, I would like to refer to the Aerospace Recommended Practice 4754A documentation. As you probably know, this document provides guidelines for the development of aircraft systems endorsed by civil aviation authorities. ARP 4754 is widely used in the aerospace industry to provide best practices for demonstrating compliance with regulations. The development process is broken down in several stages: functional development, allocation of functions to systems, system architecture, requirements allocation and system implementation, ending with documentation. It is worth mentioning that the Simulink environment provides tools to cover each of these items. there is a requirements tool to track requirements, a system composer tool for system architecture, and automated testing tools which can generate reports. I will not go into more details here, but those resources can be found online on the MathWorks homepage. What I would like to show here is that real-time testing enables compliance with ARP 4754 as all aspects of this guideline are covered. Beta Technologies is an excellent example of a company implementing this design workflow. Beta has put a lot of effort into designing an eVTOL aircraft and iterating through several designs. Here you can see their model Elia, which took off for the first time in 2020. After successfully flying the first two prototype aircraft, Beta is transitioning from a concept design into a type design phase, with the goal to certify the aircraft and deliver it to their customers. They use Simulink and Speedgoat target machines to perform development and verification tasks on their Ironbird, allowing them to keep up with the short development cycles. A development workflow has several stages. In aerospace development, it starts with a defined set of requirements. As mentioned earlier, you want to do some desktop testing to eliminate as many errors as early as possible. To test how your early design behaves in the actual environment, you can leverage controls prototyping. Once you've successfully implemented your design, you can test your controller using hardware-in-the-loop testing, as you're working partly on the actual hardware and partly on modeled or simulated components. Let's dive into these two concepts, starting with controls prototyping. In rapid control prototyping, the plant could be your aircraft or Ironbird. The development task focuses on the design of the controller. This means that the real-time target machine emulates the controller and executes the code of your embedded control design. Performing control tasks in a loop allows you to verify that the controller fully meets the requirements. Early testing of a control algorithm can help you eliminate errors. To better understand what controls prototyping looks like in real life, I would like to share this example from the Scientific Association Aachen. They are developing a hybrid electric aircraft. The baseline target machine acts as the controller and the heartpiece of the Ironbird. From the pilot's side, input commands such as throttle and elevator angle are read into the target machine. Inside the target machine, the actual motor control takes place. On the test bench, the target machine controls the motors through the inverters as well as the batteries using a CAN interface. It is quite interesting to have a look at this setup. Since they are only using a few signals, they were able to build their setup with a small baseline target machine. On the left side, you can see the BMS testing with actual battery cells. This is used to test the safety and control strategies in case a battery cell overheats, for example. On the right side, you can see the powertrain test setup with the gauges, which will later allow pilots to monitor the system. This setup allows them to conduct extensive testing at an early stage without having to build the actual hardware and talk to the authorities about potential certification ways. Once you're satisfied with the control design, you want to move to the implementation stage. Ideally, you want to have the code of your controller automatically generated based on the model of the controller you developed and tested earlier. Fortunately, this is possible. Once you're happy with the controller you designed in this controls prototyping setup, you can automatically generate the code using code generation. This can be HDL or C code. After compiling the code on your controller, you can then go ahead and test it. You probably don't want to directly put the flight controller into the aircraft. Therefore, you can conduct hardware-in-the-loop testing, where you take your physical controller and run it against a target machine, which is a physical representation of your plant. I would like to emphasize the key differences between data acquisition and hill testing. Most of you are probably familiar with some form of data acquisition. Engineers use this in their everyday life to record data, to do some post-processing and perform open-loop testing. Obviously, these things can also be achieved in hardware-in-the-loop testing, although a hill setup may be a slight overkill for these tasks. The advantage of doing hardware-in-the-loop testing is the closed-loop testing. This means that you can run dynamic scenarios and actively interact with your controller. The complete test process can be automated, allowing you to perform complex tests with a click of a button and to automatically generate test evidence using automated report generation at the end. You can test against a set of requirements and perform regression testing in case you have some last-minute changes to your code. This approach allows you to test your controller in real time, which cannot be achieved by just doing measurement or data acquisition. There are typically three main components in a hill system. First, your system under test. This includes the production controller that requires thorough testing and additional physical components like domain controllers, sensors, and actuators. Second, a hill test bench, including a real-time simulator where you can run a digital twin of the plant together with emulated plant components and I/O modules supporting data acquisition, signal conditioning, and communication with the system under test. Third, a workstation running application software that supports the setup and operation of the hill test bench. Let's look at a Speedgoat real-time system to understand what it comprises of. Each system is configured to your individual requirements about performance and I/O. Changing requirements are not a problem, as you can reconfigure I/O. You can choose from a vast range of I/O connectivity options and exchange them at a later date. All real-time target machines are expressly designed to work with Simulink and Simulink Real-Time. We not only support the current releases, but we also guarantee to support future releases. Our hardware quality, long-term warranty, and maintenance services ensure the long-term operability of your real-time testing hardware. Delivery of each real-time system includes the real-time target machine, I/O modules configured to your needs, together with accessories such as terminal boards and cables, and the Speedgoat I/O block set for Simulink. The block set library allows for seamless connectivity to the hardware. Speedgoat supports all key protocols for the aerospace industry, such as ARINC 429, ARINC 825, AFDX, or MIL Standard 1553. Overall, we support over 200 I/O modules. We also have general purpose protocols such as SPI, I2C, Ethernet, and a vast range of analog and digital protocols. You can leverage all relevant I/O protocols at the requested voltage level and sampling rate, and even perform fault insertion. These I/O interfaces can seamlessly be integrated into the workflows from MATLAB and Simulink. That should give you a good idea of the value and method of real-time testing. Now, I would like to show you an example of how a test of an electric management system of an aircraft or even eVTOL could look like. This is an aircraft emergency power system with a fuel cell, lithium battery, and ultracapacitor. The goal of the model is to emulate the scenario of an emergency landing with a generator failure. In this model, we have multiple submodels, such as the aircraft system, the model of the electric management system, and a user interface. We provide a predefined load profile of an emergency landing scenario where different things happen. After the generator fails, the electric management system has to provide enough power to cover the different loads, such as the use of spoilers or flaps. Let's have a look at how the system is modeled. Here you can see the complete system with the fuel cell, battery, and ultracapacitor. If you click on the fuel cell, you can configure it. This allows you to choose your level of fidelity. The same thing goes for the battery. You can choose the technology, all of the key parameter, or you could even define your own battery. Finally, the capacitor has some parameters too, but I'm not going into more details here. In the middle, you have the DC converters and many signals going in and out. Up here is the load profile, which we use to get the load for the landing. On the other side of the model, you have the controller. If we have a closer look, you can see that in this example we provide several options for the controller to choose from. For this demo, we choose an easy PI controller. Since we don't have an actual controller available, we simulate both components, the plant below and the controller above, using the Speedgoat hardware. They talk together via a real physical communication protocol, in this case the ARINC 429. The signals are sent out from the plant into the controller and afterward backwards from the controller into the plant. In this ARINC send block, you can see how the protocol is constructed. We send the parameters which come out of the model and we encode them according to the ARINC standard. The standard allows for several communication level settings which can be set in these parameters here. This same application may also run on CAN or different protocols, such as time-sensitive Ethernet, for example. Now let's run it. We connect to the target and click Run on the target. Once this is done, the code is automatically generated and loaded to the target machine. This easy feature is also what makes this workflow great. You don't need to generate any configuration files or copy any commands. The hardware is completely integrated into the Simulink environment, which means that you can completely focus on the system you need to develop and not on the test tools. Okay, below here you can see that it is compiling. We can also check in the diagnostics viewer that there are no issues or warnings with the model. Once it's done compiling, the application starts automatically. Now we will be able to see the signals on the user interface here. The overall load is blue. Right now it's 0. The fuel cell provides some power to charge the battery. Therefore, the purple line is negative. After a short while, we will see that the generator is lost. You can immediately see that the load spikes, and so does the ultracapacitor. Since the ultracapacitor is the fastest element, it reacts first. Then the outlet of the capacitor is reduced and the main load is taken by the fuel cell. The battery is stable at the maximum outlet. When the load drops sharply, the ultracapacitor takes up this transient behavior by actually being charged, while the battery stays constant for a short while. Now, with the load further dropping, the fuel cell can provide enough energy to charge the battery again. With this small load, you can see that the plane has landed. While it is on the ground, the fuel cell is used to charge the battery. Below, you can see more elements like state of health of the battery. In case you want to inject different behaviors, you can also override the load manually during the simulation here. This allows for maximum testing flexibility even during an ongoing test. That is the end of the simulation. A potential next step, which I'm not going to show here, is the automated report generation and requirements testing based on this hill run. This workflow allows to test different control strategies efficiently and ultimately validate the system against these requirements. Another great example from the industry is hydroplane. The goal of hydroplane is to integrate a hydrogen fuel cell into an airframe and fly the aircraft with this new propulsion system in 2023. Hydrogen fuel cell powered aircraft will have an important role in the next generation of aviation, since they are carbon neutral and do not suffer from the energy density challenge that battery-driven aircraft do. In order to meet their ambitious goal, Hydroplane needs to integrate sensors, controls, compressors and more into their new powertrain system. Hydroplane decided to use Speedgoat to analyze signals quickly and test their system. This allows them to build up their test setup quickly and gradually expand it as they progress in their project. To give you an overview of the tools available to help you during your development process, we created the summary of aerospace-related toolboxes and block sets that run in the MATLAB and Simulink environment. They work hand in hand with the ARP 4754 guidelines I showed earlier. Besides those powerful all-round tools, specific commercial off-the-shelf software functionalities are available, such as the Aerospace Toolbox and the Aerospace Block Set. Further, commercial off-the-shelf software functionalities, such as the UAV or radar toolbox, are available. Leveraging this versatile variety of functionalities ensures to provide all the tools required for your specific project and needs. One important aspect in both conventional aircraft development and VTOL or eVTOL development is the design of the batteries and battery management systems. Using the BMS controller Hill setup, you can configure the battery on your host computer and run the emulation on the connected BMS Hill rack. So, how can you test your batteries and BMS systems? The typical task would be to monitor or balance cells, control the state of health or the state of charge, and perform thermal management. Also, inserting faults is a rather large topic. Speedgoat allows you to deploy your Simscape electrical model in real time to perform all those tasks mentioned earlier. The test rack can be customized to contain a battery cell emulator, fault insertion units, or even units to perform temperature emulation. This battery management testing capability using a cell emulator can be really useful to shorten development cycles of your BMS and battery, and again to find errors earlier. Therefore, I want to show you how you can build it up. In the middle, we find the battery cell emulator, which emulates the currents and voltages of the digital twin and exposes them to the outside. Each battery cell emulator can emulate up to 12 individual cells, and one can stack several units, therefore enabling the emulation of all sorts of battery systems, from small to large high voltage systems. You can simulate any battery cell type with voltages up to 8 volt. Each individual cell channel can source and sink continuous currents up to 5 amps and integrates current measurement based on Coulomb counting, enabling measurement of charge and discharge currents with outstanding accuracy. These are some helpful components which can be integrated into racks. Besides the high voltage terminal board and safety features, you can also tailor the size and required voltage. The system is EMS tested and complies with common safety standards. After having developed and tested all of these great controllers and hardware, you want to claim some certification credit for it. It is crucial to follow the processes to achieve certification of your product. There are many different standards and guidelines that support you through this process. If you look at the process from a top-down approach, you start with the design of the overall aircraft and define systems and system boundaries, while doing some safety assessment according to ARP 4761. Then you move on to the development of these subsystems. We looked at ARP 4754, which is the guideline for development of civil aircraft and systems, addressing the complete development cycle from systems requirements through verification. Depending on your subsystem, you follow the DO-178C process for software development or the DO-254 process for electronic hardware development. Both are supported by tool qualification. DO-330 or model-based development for DO-331 for airborne equipment. Today, we will only focus on DO178C and DO254 as they are the most widely used in the industry. Those standards were written in the same framework, although the DO178C was earlier. In both cases, we start with requirements capturing. Those are usually implemented doing textual requirements capturing. After knowing the requirements, you move on to conceptual design and low-level requirements. In both hardware and software cases, this can be done using Simulink models. From Simulink, you can automatically generate HDL code for your hardware or C code for your software. This leads to a detailed design or source code. The HDL code leads to the netlist and routing, which can be manually reviewed if this is required in your certification process. Until the modeling part, both standards are equivalent. Depending if you are doing software or hardware design, you will use different models transformations. Depending on your project, it may be not straightforward on how to claim certification credit for the model-based design approach. The standards DO330 and DO331 provide further clarification. In recent years, MathWorks and Speedgoat have helped numerous customers achieve tool qualification and certification using the model-based design workflow. It would be beyond the scope of this webinar to go into the details on how every step along the way looks like, but don't hesitate to check out our websites or reach out to us directly if you want to go deeper on this topic. It is worth mentioning that the DO qualification kit allows you to do tool qualification. The verification tools themselves are qualified. To use the tools in your tool chain, they can be qualified, but it's not compulsory. For example, you could review the generated code instead. It is also possible to only qualify certain features of your tool. There is guidance about tool qualification in the ED12C standard, providing information about which tool qualification level is used to obtain the required design assurance level. At the end, I would like to zoom out a bit again and give you an idea of how your company could integrate model-based design in their development and certification workflow. Implementing this new approach may not be straightforward at first, as creating models will take some time and require new skills. So, there is an initial investment for every company planning to implement this. Many aerospace companies work under a lot of time pressure to achieve certification and sometimes don't take the time for the implementation of better workflows. They are often punished later on. Therefore, it's a good idea to start early. This summary from Airbus shows how they overcame the initial fear of the new approach by pointing out the benefits. Alonso Parto presented this graph at a MATLAB symposium. I find it quite interesting because it shows how you can increase flexibility and reusability using model-based design. Finally, engineers can detect design failures earlier and focus on understanding the systems instead of building models and worrying about interfaces and documentation. Now, this should give you a pretty good idea of how to use real-time testing to develop your controller as demonstrated at the beginning. I hope that you have learned how model-based design can help with rapid control prototyping and how real-time testing allows for hardware in the loop and ultimately automated testing of your airborne controller. Thank you very much for your attention.
You want to learn more about real-time controls testing? Then find additional content linked here.